All right, welcome AP students to your AP Redox problem. We're going to go through 3 conceptual questions, and I'm actually just going to address part A of 3 various types of questions that are rooted in understanding standard reduction potential, and then we'll head into an AP question. So go ahead and look in the description if you want to feel pretty good about how to reach standard reduction potentials. You're welcome to skip over this part and I'll put the timestamp for when the AP problem starts in the description. Okay, so for question number 9, determine whether a spontaneous redox reaction will occur. If so, write the balanced chemical equation using standard reduction potential table in the notes. So one thing that you have to remember is when we talk about spontaneous or thermodynamically favorable redox, we really want, when you look at the table, we want our reduction element to be above our oxidation element, okay, in order for it to be spontaneous. Why does this make sense? It's because when you are reduced, you want the species that's being oxidized to spontaneously donate the electrons to the reduced species. And in a way that I think hopefully I mentioned in class is that you can kind of think of it like a balloon. Like if the species that is being oxidized packages up its electrons to be transferred to the reduced species, what would happen naturally is that the electrons would float up to the reduced species or the species undergoing reduction. But that's just kind of analogy. And of course, the opposite way of thinking about it is if you have to shove your electrons down, you have to put energy into it. And by the way, that's a hint at electrolytic cells. You have to put energy into it, and therefore it's not spontaneous because you're putting work and force into shoving the electrons down if the element that's being reduced is below the element that's being oxidized on the standard reduction potential table. So we, of course, want above. We want our reduction species above, and for those electrons from the oxidized species to float up and be caught by the reduction species as an analogy. So that being said, when we look at the table, what we're trying to see is, will a spontaneous redox occur between these 2 compounds? For the first thing that we got to do is figure out, well, which compound is more likely to be reduced, which compound's more likely to be oxidized. And what we see is when you look at the table in your notes, when you look at the table in your notes, we see that F2 is right at the top, okay, right at the top of the SRP table. And what that means for us is that it's the most likely to be reduced, okay? F2 will lose 2 electrons to go to 2F minus. And it has an electron potential, standard reduction potential value. Goodness gracious, I'm jumping ahead in my brain. Standard reduction potential value of positive 2.87. And we like positive. That means it's more likely to be reduced, right? So what we see is that iron, oh my God, it is too early in the morning, that diatomic fluorine is going to be most likely to be reduced. Okay. On the other hand, what we see is that aluminum 3 plus, all right, let's find that. We look down the table. Don't forget, I kind of had to split the table for the sake of space. So I have to go down here. Aluminum 3 plus is, it is also reduced, okay? And so the problem with this is that we can't flip it because what we have is aluminum 3 plus that's also on the left side of the column, therefore saying that this species will only undergo reduction if we're talking about this specific compound form. So what we notice is aluminum 3 plus also undergoes reduction. Not as likely though as F2 because it's lower. Not as likely. But what we see is that we can't have a reduction with a reduction. So this would actually be a no reaction. Example. Okay. Okay, so now let's look at question number 10 in our next series of conceptual questions, where we're asked to predict whether a single replacement reaction will occur. And then if so, write the balanced net ionic equation. So first things first, with single replacement reaction, we need to determine the ions involved. So that we need to determine the net ions involved in the equation in the first place. So what we're going to see is that for the single metal replacement between aluminum and CuSO4, we see that aluminum solid would react with CuSO4, most likely aqueous, because we don't really react ionic compounds unless they're in water. It's just because a solid lattice structure is very non-reaction favorable. And what we would see is it would go to produce Cu solid and aluminum 2 SO4 3 as far as charge canceling. And then of course we'd have to balance this equation. So we would see that we need 3 coppers and 2 aluminums and 3 CuSO4 if you were to balance all of this in order to follow the law of conservation of mass. Now what we're going to do is we're going to break this up into the respective ions, and that will help us identify which species is actually being reduced and which species is actually being oxidized, or the net species. So notice we have SO4. SO4 will end up being actually our spectator ion when we look at the net ionic equation occurring between this redox process. And what we see is that SO4 is the spectator. So because SO4 is the spectator, we're now going to write our net ionic equation with respect to just the ions involved in the redox that are actually seeing electron transfer. And we see that it's 2 aluminum solid and 3 copper 2 pluses, right? Producing 3 copper solids and 2 aluminum 2 pluses. All right, aqueous. And so what we see then is we definitely see in this redox, if this redox were to occur, aluminum would have to be oxidized and copper 2 plus would have to be reduced. So now we need to look at our SRP table and say, well, according to the table, do we see that copper that's undergoing reduction in this process is above aluminum that would be oxidized, or do we see that it won't occur because it's actually flipped and therefore unfavorable? So let's go ahead and look and see if aluminum is above copper 2 plus, and it's on the opposite sides of the table. So when we look at that, we see that aluminum is, oh man, table. Here we go. Aluminum solid is oxidized, and we see, oh, it does fit. It fits. We have on this side of the table, if you're toward the left and toward the bottom, you're more likely to be oxidized. And then copper 2 plus, scroll up. You see that copper 2 plus is above, and it's supposed to undergo reduction. It's above the aluminum and on the left side of the table, making it more likely to be reduced. So we do see a favorable pairing of oxidation and reduction, where the reduction element is above the oxidation element, therefore being a favorable and spontaneous process. So we would say then that the reaction will occur, okay, spontaneously, okay? And I wrote out just naturally in the process of figuring out the necessary ionic elements, I naturally wrote out the balanced net equation. So, all right, so let's go ahead and look at now short FRQ question number 2 on page 11, AP question. We're given 2 half reactions, and we're given the prompt that in human cells, a compound known as NADH is involved in a reaction that generates an electrical potential. The reaction is based on the 2 half reactions shown above, and the balance equation is provided. First things first that you should notice, which I already kind of wrote down, is that according to the balanced chemical equation, we actually flip the NADH half reaction because it is oxidized. It serves the role of oxidation in this redox reaction, and therefore we would flip the standard reduction potential value to become positive. But that's just something to notice. And then you, of course, were told in the prompt to justify using the half reactions or the balanced chemical equations, which are constructed from the half reactions, and the oxidation state number in oxygen. So what you see here is that the oxidation states for oxygen, each oxygen atom in diatomic oxygen is 0. And for the single oxygen atom in H2O, it's -2. So what we see is that oxygen is oxidized, or yeah, sorry, not oxidized, reduced, going from a +0 or a +0 to a -2 oxidation state. But according to the half reaction, we're actually told that in order for this to be electronically balanced, we see that 4 electrons are transferred. So that means that the answer to our question is 4 moles of electrons, right? 4 moles of electrons are required to convert, okay, to convert 2 moles of oxygen atoms. Where did I get the 2 moles of oxygen atoms? Well, if I'm looking at each individual atom of oxygen, for every diatomic oxygen, for every 1 mole of diatomic oxygen, I needed 2 moles of actual individual oxygen atoms, because it's 2 oxygens required, double bonded to each other, to make 1 diatomic oxygen. Okay, so I need 4 moles of electrons to convert 2 moles of oxygen atoms in 1 mole of diatomic oxygen in order for it to change oxidation states 0 to positive G will occurs, -2. Okay. Now we're asked for part B to calculate the electrochemical potential for the overall reaction. So I've already kind of done the work because that's the first thing I saw. Is when I see data in the AP exam, you should immediately think, okay, what is this data telling? Like, what's the big, quick 10-second scan? What do I immediately notice? Okay. And what we see is that for the electron potential of the cell, we would actually flip the NADH, and notice, remember, for electrochemical values, standard reduction potential is an intrinsic value, so we do not multiply in order to like account for the stoichiometric ratios. Like, we do not multiply because it is an intrinsic property. The only thing we do is flip to acknowledge the reduction versus the oxidation behavior. So we would see that the electrochemical cell potential for this redox reaction would be equal to the sum of the reduction half reaction potential and the oxidation half reaction potential, which would be positive 0.815 plus, all right, 0.320. And we would get that we have a value for this overall redox reaction as positive 1.135 volts, which is quite favorable. And finally, for this short FRQ, oh, gee willikers, sorry. Finally, for the short FRQ, we are asked to calculate the value of G for the overall reaction. So here we're going to use the G equals N negative NFE, okay, NF E equation, and what we're told then is that this is equal to, we have 4 moles of electrons being transferred. So we would put -4, right, times Faraday's constant, which is totally given to you on your handout. And that is equal to 96. And then I forgot my units. What am I doing? -4 moles of electrons per reaction, right? Per mole of reaction. Look at me getting lazy. Times Faraday's constant, which is 96,485 coulombs, which is a charge unit per mole of electrons, times the electrochemical cell potential, which is 1.135 volts. And by the way, a volts is equal to joules per coulomb. So in order to follow the trend of proper charge canceling, we would do joules per coulomb, and we'd see that our overall value, our moles of electrons cancel, our coulombs cancel, and we get a certain amount of joules, and which is Gibbs free energy unit per mole of reaction, would be -4.380 times 10 to the 5th joules per mole of reaction. And of course, you are welcome to convert that to kilojoules. So -438.0 kilojoules per mole of reaction. And that would be our final answer for this part of the short FRQ. Lot of unit conversion. Remember, if you track your units, it'll pretty much tell you whether or not you're setting up the on top versus the on bottom correctly, and you're getting an answer that has the proper meaning of the desired meaning that you want. So remember D, you're gonna have to come back and do it on your own when we talk about non-standard electrochemical cell conditions. But otherwise than that, good job, you guys, and best of luck.